So the next transmission line I would like to bring to your attention is basically the coplanar waveguide line. Now the coplanar waveguide line is actually trying to address some of the drawbacks of the microstrip line and is a very, very interesting and a very, very popular line. So first of all, let's look at its geometry. So it still has a strip to carry the signal, but instead of having the metal on the bottom side of the substrate, it actually brings the metal on the left and the right side. Sorry, I should say the ground. So this is the ground, and it's a symmetric line in the sense that there is a ground plane on each side of the strip line. And the key difference compared to the microstrip is the ground now is on the same side of the strip line. The picture on the left-hand side, picture A here, is actually the ideal coplanar waveguide line that actually assumes an infinite metal. But in real life, of course, we do need to have a finite ground. And when you have a finite ground, you have to cut it somewhere. Usually, we try to allow enough space such that this finite ground width is approximately 3 times the width of the strip. Now, sometimes we can't afford that much space, and sometimes people will push this down all the way to even having the same width as the strip, and it still works. It's higher loss, and it's a more dangerous design, if you will, for non-ideal effects, but it will still work. Now, this line sometimes will also have a ground plane on the bottom side, either because we want it or because it's for free. Maybe, for example, this ground plane is actually the package of the circuit. And in that case, it will actually called a grounded CPW line or a grounded coplanar waveguide line. Now, let's see some of the main advantages of this line compared to microstrip. The first advantage, as I would like to say, is that sorts become incredibly easy. So here, we just got a sort. All I have to do is connect my strip line to the ground that is literally right next to it. And that distance can actually be very, very small. That distance could be actually micrometers or millimeters. And that means that that length now of the sort is up to me to decide, is not dictated by the substrate. So sorted lines become very, very easy. Second advantage I would say, which is also very important, is that you don't depend on the substrate anymore. So schematically, I will put it, it's not a function of the thickness of the substrate, to be more precise, and I mean that thickness here anymore. What I mean by that is that the impedance of the line now is not dependent on how much H is, but it only depends on what's the ratio between W and S, where S is the spacing between the strip and the ground. So you choose the ratio of W by S, and you can basically get impedances that you like. A few more advantages that are a little bit harder to see. One is that your effective dielectric constant here is almost exactly the average of the one in air and the substrate. The reason for that becomes evident if you actually see the electric field between in the CPW line. It turns out that almost half of the field lines are in air, and almost half of the field lines are actually in the substrate. That makes the effective dielectric constant actually to be almost half of it. And even better than that, as we'll discuss later on, that is true for a very wide range of frequencies, which actually makes the dispersion of the CPW line to be lower than the dispersion of the microstrip line. And for that reason, the CPW line is actually often preferred in high frequency applications than the microstrip line. Now let's talk about some of the drawbacks. Nothing is free in life, unfortunately. So here are some of the drawbacks. One drawback which is very easy to see is size. Now when I have to make essentially a transmission line segment, I don't have to put just the strip, I actually have to carry my finite grounds right to the left and to the right. That means the actual footprint becomes much, much larger. The second thing is I really have to pay attention to symmetry here. What I mean by that is that in the microstrip line, it was enough to just drill a hole and connect the strip line to the ground. Now, what I actually did here was incorrect. If I need to make a sort, I have to make a symmetric sort. So I have to connect my strip line to both the left ground plane and the right ground plane. If I avoid doing that, or if I forget to do that, I actually have a multi-mode transmission line where now the potential of the left ground and the right grounds are not the same, so they will actually start having feed lines from one to the next, which is an additional mode. So I start having multi-mode transmission lines, and that's a mess. So I have to be a lot more careful on preserving symmetry, and I have to be a lot more careful, and we'll see examples later on as well, making sure that the two potentials of the two ground planes are essentially identical. So we could discuss this more, but these are the main ones I want to bring to your attention. I also wanted to say something that it's a little bit of a funny story of how the coplanar waveguide came to get its name. First of all, this line was invented in 1969. And this lecture is recorded in 2019, so we're literally celebrating 50 years of the invention. So as you can see, it's not really that old. I know none of you were alive probably at the time, but 1969 is only 50 years ago. The inventor of the line is actually still alive. He lives in Beijing, enjoying his retirement. He actually invented this line when he was working for the RCA Sharnoff Labs here in the United States. And his name is interesting, is Cheng P. Wen, which it might not tell you too much until you check this CPW. So it's actually an interesting coincidence, perhaps. In fact, the story goes that when Dr. Wen invented the CPW line to address some of the issues with the microstrip line, he actually called it planar strip line. He didn't call it coplanar waveguide. But one of his colleagues actually said, well, we should call this coplanar waveguide. I guess it was convenient. So essentially, in 1969, CPW invented CPW. And I have actually had the pleasure of meeting him a couple of times in conferences. That's one of the benefits of actually going to conferences. You can see some living legends in the field. Now, let me give you some layouts that can a little bit train your eye of how we basically utilize this type of a CPW line. So you can see a good example here of how we can make a short circuit. So look at the center. The strip line actually is now shorted to the grounds at the end. This is an impedance step. This is an interesting thing. As I mentioned before, it's only the ratio of W by S that determines the impedance. So here we actually change this S rather. W is the same, but the spacing S has actually been changed. So essentially, if you look at this layout and you want to make the equivalent schematic, it would actually be a transmission line with an impedance of Z0, possibly going to a transmission line with an impedance of Z1. Now, I'm going to come back to C, but let's look at D. Here's an example of an open circuit. So you just literally stop the strip line. This is an example of a capacitor down here. In fact, all you have to do to make a capacitor is basically place a gap, an air gap. Just put a break, and that distance between the break will actually give you a capacitor. Here's a good example of a series stub. So look at this length. This is the length of the stub that you will have, and so on and so forth. Now, it's also worth spending a little bit of time of understanding angles. So what happens when you have to bend a circuit? It's not as simple as it might think. In microstrip lines even, we have to be careful. But in coplanar waveguides, we have to be particularly careful because of one effect that is a direct consequence of the geometry. And this is the fact that the signal that travels through this ground plane has to make that distance, while the signal that travels through the other ground plane has to now cover this distance. And it doesn't take much training to realize that these distances are not the same. And so that basically means that now the phase of the signal at this location, if it were the same as the phase of the signal at this location, is not true anymore. The phase of the signal here, unfortunately, is now not the same as the phase of the signal there. And that creates imbalances. That creates these additional modes that I mentioned before. So bending coplanar waveguides is not simple. So how do we correct this? There are different ways we can actually correct that. Probably the most common way, which we'll also see some pictures later on, is by including straps. So we just literally take maybe a wire bond or some other type of a strap, maybe a silicone little wire, and basically literally short them together. Let me see if I can put it in a different color so you can see. So there will be a little bit of a strap here and a little bit of a strap here to make sure that the two potentials are actually equalized. There are also other techniques which I won't really discuss too much in this class. For example, this type of geometry you will see. This type of geometry you will even see when you just bend microstrip lines. You will see things like this, and not in layouts things like this, because they create essentially interesting edge effects that we don't want to deal with. So this is a little bit of a layout training of some of the main practical applications or issues that you need to be aware of.